Welcome back to the deep dive. Today we're cutting through the noise, really getting into the weeds on a document that defines the future of an entire vehicle segment.
That's right. We're not just looking at a document today. We're taking on a role. We are the chief systems engineers at a top-tier global automotive consultancy.
Right.
And our mission, our entire focus, is to break down this engineering requirement specification, the SOR, for a next-generation micro-low-speed electric vehicle, a micro LSEV.
And this document, it's basically the blueprint for survival, isn't it?
It is. This is the whole ballgame.
Okay, so let's unpack the core challenge here because this might be one of the hardest vehicles to engineer successfully.
I think it is.
Why is that? Because you're fighting the most stringent safety and efficiency regulations on the entire planet, all while trying to hit a price point where every single dollar, every cent counts. This isn't about luxury. It's not about 0 to 60 times.
Huh?
It's about solving that fundamental global mobility problem safely, cheaply, and, as efficiently as possible.
And the source material we're working from, it's a very detailed engineering and regulatory roadmap. It applies what we like to call McKinsey-style thinking to completely overhaul this LSEV market.
That phrase, McKinsey-style thinking, I think that's key here. We're talking about a transformation, right?
A total transformation.
Yeah.
We are moving this entire segment away from being a regulatory novelty product.
You mean glorified golf carts?
Basically, yeah. Things that used to just skirt the edge of vehicle laws. And we're moving it toward a platform built on true car-spec lean manufacturing.
So our goal for this deep dive is to define the core vehicle technical specifications, the VTS.
Yep.
And, this is the big one, provide the unassailable justification for adopting a 96-volt high-voltage powertrain architecture.
And that's the linchpin of the whole strategy.
And the constraint that drives every single one of these decisions. It has to be global homologation, certification across the world's most, frankly, conflicting and demanding regulatory zones.
Yeah.
China, the EU, Japan.
It's a tightrope walk, a real tightrope. If we get the voltage wrong, the cost model collapses. If we compromise the structure, we fail safety compliance in one market or another.
There's no room for error.
None. It demands laser focus. We can't afford any arbitrary decisions. Every single component choice, every system spec has to balance those three conflicting demands: regulation, safety, and a ruthlessly tight cost target.
All right, let's start with part one then, the strategic imperative. Why now? Why is this engineering transformation so urgent? What was so fundamentally wrong with the old LSEV model that we have to, scrap it entirely?
Well, the old model is, to put it bluntly, commercially non-viable and legally obsolete. It's dead.
Okay.
When we talk about the old model, we mean these vehicles built on simple, low-automation tubular steel frames.
Right, the go-kart chassis.
Exactly, with basic plastic bodies and, most importantly, the extreme weight and terrible energy density of lead-acid batteries. The regulatory loopholes that let those things exist, they're closing. Fast. In every major market.
So the regulators are just demanding that these little cars stop being toys and start being, actual safe vehicles.
They're forcing the segment to grow up overnight. And that's forcing a move to what we're calling car-grade standards.
That sounds expensive. How do you do that without pricing yourself completely out of the market?
Well, the forcing function isn't just regulatory. It's also competitive. You have to look at the new baseline that's been set by the market leaders.
You're talking about the Wuling-Hongguang Mini EV.
Specifically, its third generation. That vehicle completely shifted the paradigm. It wasn't built like a scooter. It uses a high-rigidity structure with, I think, 67% high-strength steel HSS.
And it has modern safety features, active and passive.
Right. Wuling proved you could deliver real safety, real durability, and better features at this incredibly low price point.
Yeah.
So if our proposed vehicle offers anything less than that, it's immediately irrelevant, non-competitive.
Okay, so if Wuling set that bar, the SOR we're developing has to leapfrog it, especially on efficiency and speed. What's the core technical strategy that the report recommends to make that leap while still managing the cost?
The core strategy, and this underpins every single decision we're going to talk about, is the adoption of a very specific voltage band.
Okay.
We're talking 96 volts to 144 volts for the nominal architecture. And that decision is strategically paired with LFP lithium iron phosphate cell to pack, or CTP battery tech.
And a specific motor type, too.
Yes, and highly efficient permanent magnet synchronous motors, PMSM.
Wait a second, hold on. Why that precise voltage? 96 to 144 volts. Why not just stick with the lower 48 volts for simplicity? Or, jump all the way up to 400 volts and use existing high-volume EV components?
Because that's the critical strategic insight.
You're saying this intermediate voltage is the secret sauce?
It's the only way to thread the needle between two conflicting but equally essential global requirements. On one hand, you have the brutally tight energy efficiency targets in China. We're talking about getting consumption under 9 kilowatt hours per 100 kilometers.
That is ruthless efficiency.
It is. And on the other hand, you have the expectation for higher utility and speed in markets like Europe, where the vehicle absolutely has to be capable of sustained speeds over 80 kilometers an hour just to function in traffic.
And that's the crunch, right? High speed needs high power. High power at low voltage means insane current and huge losses.
Massive losses. Or at 400 volts, you're looking at really expensive high-voltage components that destroy your cost structure.
So this is the compromise.
It's the genius of it. LFP gives us the stability and the cost. The PMSM gives us the efficiency of partial loads, which is most of city driving. But the 96-volt architecture is the economic sweet spot. It manages the current effectively without demanding the prohibitive component costs of a 400-volt platform.
So it's the trifecta: cost, performance, efficiency.
It is the cheapest possible way to deliver 100 kilometer per hour performance while simultaneously hitting that sub-9 kilowatt hour efficiency mark. It's the only way to survive in the post-2025 micro-EV world.
Okay, so that sets the stage. Let's move to the constraints. We can't design a single part until we fully define the legal box we have to fit inside globally. The strategy here is, frankly, brilliant, a smart platform architecture. We anchor the core design to the most stringent standard, which is China's M1 microcar category.
Right.
But we keep the flexibility to, cost down the configuration to meet less demanding standards, like the EU's L7E.
And that approach maximizes our market reach while minimizing design redundancy. It's critical. If we started with the simplest standard, like the US LSV, we'd be instantly irrelevant everywhere else in the world.
So you have to start with the toughest requirement.
You have to start with the most demanding requirements for safety and efficiency and make them intrinsic to the platform.
Let's start with China then. Why does this report label it the uncompromising global benchmark?
Because China is, right now, the global forcing function for technical excellence in the EV space. Starting January 1st, 2026, they're implementing the world's first mandatory EV energy consumption standard, GB 36980.1/2025.
And that's not a guideline.
Not a guideline, not an incentive. It's a hard barrier to entry, full stop.
Yeah.
If you don't comply, you cannot sell the vehicle.
And for a micro vehicle in our target class, what does that standard actually demand?
For a vehicle in the 700 to 800 kilogram curb weight class, the official limit is expected to be under 10 kilowatt hours per 100 kilometers.
Which is insane.
It's like running an internal combustion engine on fumes.
Yeah.
And our VTS is even more aggressive. We're targeting less than 9.0 kilowatt hour each 100 kilometers on the CLTC cycle.
Why so aggressive?
To create a competitive buffer against the market leader, Willing, which is already at about 9.3. And achieving that demands a level of powertrain optimization that it eliminates everything but a top-tier system. PMSM, low rolling resistance tires, hyper-aerodynamic design, the whole package.
A brutal efficiency target. But the pressure doesn't stop there, does it? Safety, especially battery safety, is being enforced with similar rigor.
Absolutely. The other massive hurdle is the battery safety standard, GB 388.031/2025. And this is the cornerstone of our chemistry decision. It introduces what we internally call the no-fire rule.
The no-fire rule. Explain that.
The battery system has to be designed to actively prevent fire or explosion for at least 2 hours, or ideally indefinitely, after a single cell goes into thermal runaway.
2 hours? For a lithium-ion thermal event, that sounds almost impossible at this price point. What does that one rule force us to do from a chemistry standpoint?
It is the single biggest technical mandate forcing us to adopt LFP chemistry over NMC.
Nickel, manganese, cobalt.
Right. LFP lithium iron phosphate. It has an intrinsically more stable crystal structure. That phosphate backbone holds onto its oxygen atoms much better, so when it fails, it releases significantly less oxygen and heat than an NMC cell.
So if you tried to meet that 2-hour rule with NMC,
the cost would be prohibitive. The necessary intercell insulation, the cooling systems, the fire suppression materials. It would add so much complexity and cost that the entire micro-EV project becomes uneconomic. Instantly. LFP is the only technical and financial choice.
So China is using these standards not just to mandate safety, but to effectively engineer the vehicle's core components for you.
Exactly, and it goes beyond that. Even the tax incentives are strategically linked to performance metrics, tax exemptions in the coming years. They're explicitly tied to achieving a CLTC range over 200 kilometers and meeting a minimum system energy density.
So it prevents stagnation. You can't just sell a cheap, low-range product forever.
It forces continuous technical improvement across the board.
Okay, let's pivot to the EU. The market there is built around the L category for quadricycles. What are the constraints there, and where is our opportunity?
Well, the L category is split, and we have to be careful. L6E, the light quadricycle.
That's the Citroën Ami category.
Yes. And it's just too limited for our global ambitions. You're looking at a 425 kilogram curb weight, a max speed of 45 kilometers an hour, and only 6 kilowatts of power. That's strictly for, neighborhood trips or closed communities.
So L7E, the heavy quadricycle, that's our strategic sweet spot.
That's it. L7E gives us a higher curb weight of 450 kilograms, and that excludes the battery mass, and a much more robust 15 kilowatt power limit. Speed is theoretically unlimited, but that 15 kilowatt really caps the practical top speed around 80 to 90 kilometers an hour.
Which is viable for city expressways and peripheral roads. That's where we need to compete.
Precisely.
But the report flags a huge vulnerability with L7E. The safety gap, right? The one exposed by organizations like Euro NCAP.
This is a critical risk, and we have to mitigate it preemptively. Recent Euro NCAP tests, they exposed what they called severe deficiencies in current L7E models.
What was the main finding?
Catastrophic structural collapse.
Yeah.
In a 50 kilometer per hour frontal impact, which is a relatively low speed, the occupant survival space was entirely compromised.
Right.
These vehicles just weren't designed to survive even moderate collisions.
That's completely unacceptable for a product we want to sell globally. We can't wait for the law to catch up. How does the SRR mandate we fix this?
The strategic insight here is to ignore the minimum L7E safety standard. We just have to. Instead, we must design the structure to reference the performance of actual passenger car standards.
Thus you're aiming higher.
We're aiming at UNIS R137 for frontal collision and UNIS R95 for side collision. These are the M1 passenger car safety goals.
So we're basically engineering a chassis that's intrinsically safe, even if the L7E category doesn't strictly demand it yet. Why is that so important from a competitive standpoint?
It gives us a core competitive advantage against two groups. First, all the existing unsafe L7E competitors, and second, against the entry-level M1 cars like the Dacia Spring. If our little micro EV can show crashworthiness that's comparable to a small family car,
that removes the biggest consumer objection to this whole segment.
It completely changes the conversation. It's also insurance against the inevitable future regulatory tightening. It's a huge market differentiator.
So to sum up the EU, it defines our speed and power targets, but the market reality forces us into car-grade structural safety.
That's the perfect summary.
What about the other markets? Japan and the US seem like the outliers.
They are the extremes, yes. Japan is highly regulated, and the USA is, in this segment, highly restrictive.
Japan is famous for the Kai car standard. That's a tough nut to crack.
It's a very high bar. Full M1 level safety, but with these very strict dimensions, under 3.4 meters long, 1.48 meters wide, and a 47 kilowatt power limit. It's tempting, but it requires a very tailored platform, which adds cost.
But there's another category in Japan, right? The UCM.
Ultra-compact mobility. The Toyota C+ Pod is the classic example. It shows a different regulatory path. UCMs are tiny, under 2.5 meters long, slow, at 60 kilometers an hour, and interestingly, they often use a higher voltage, like the C+ Pod's 177-volt architecture.
What's the lesson from that?
It proves other architectures exist, but it falls short of our mandated 100 kilometer per hour global requirement. Our platform has to be more robust.
And then there's the US market, which seems simple with FMVSS 500.
Simple, but the most limiting. The U.S. low-speed vehicle regulation caps the maximum speed at 25 miles per hour. That's 40 kilometers an hour.
So if we design for that,
the product is just a very expensive golf cart upgrade. It has no utility in the global market.
Okay, so given that we're spending millions developing this world-class 100 kph capable platform, is the U.S. market even worth the effort?
Oh, absolutely.
Sure.
But the strategic decision is critical. We do not design the platform for the U.S. We design it for the competitive global markets, China and the EU. Then, to comply with U.S. LSV rules, we use a simple, cost-effective electronic restriction.
A soft limiter in the software.
Exactly, a software fix. This ensures we maintain global scalability, and the U.S. just becomes a bonus market that requires almost no engineering customization. The car itself must be intrinsically capable of car-level performance.
Okay, that makes perfect sense. This is where we translate all those constraints into hard engineering numbers. This is the VTS, the Vehicle Technical Specifications, the constitution of our project.
This is where we define the compromises and the ambitions needed to meet that global mandate.
Let's start with dimensions, mass, and layout, the principle.
Right. Mechanical space minimization, occupant space maximization. It's the fundamental goal of any micro-vehicle design. Every centimeter you save in the mechanicals is a centimeter you gain for the user or for the battery.
And the layout decision is huge. The Amiens C+ pod went for a 2-seater. Wuling went 2+2. For a global market, which one does the report mandate?
The Wuling 2+2 layout is non-negotiable. It has to be. For global utility and market acceptance, you need it. In many regions, this is the family's primary transportation. A 2-seat layout just kills its utility. The 2+2, even if the back seats are small, offers crucial flexibility for kids or occasional passengers.
So to fit 4 people, even minimally, and meet the safety goals, what target dimensions are we looking at?
We've found an optimal sweet spot. The target length is between 3,100 and 3,200 millimeters.
And that's strategically longer than the tiny city cars.
It has to be. That extra length is essential for 2 things. 1, the rear seating, and 2, and this is critical, the crash absorption zones. We need that crush space to have any hope of referencing the UNES R137 frontal standard.
Okay, and width?
1,500 millimeters. We're maximizing shoulder room right up to the L7E limit for occupant comfort.
And height is 1,600 millimeters. Why so tall?
That's a critical design trick for maximizing battery space. We mandate a high H-point seating position, where your hip sits relative to the floor. By sitting the occupant higher up, their legs are positioned more vertically.
Which shortens the 4 space needed for their legs.
Exactly, and that frees up precious floor space for that big, flat, centralized battery pack.
Now wait. Safety structures and batteries add up fast. Our target curb weight has to be aggressive to hit that sub-9 kilowatt efficiency target.
The target is strictly less than 750 kilograms. And to hit that while also incorporating over 60% high-strength steel for safety, we have to rely on material optimization.
So what's the mandate?
A high-strength steel skeletal structure. The core safety cage, paired with cost-effective lightweight engineering plastics like PP or ABS for the outer body panels. Fenders, bumpers, non-structural door skins. This maintains the safety integrity while drastically cutting the mass.
All right, let's talk dynamic performance, range, and efficiency. What does this vehicle actually need to do in traffic to justify all this engineering?
First, top speed, 100 kilometers per hour. That is the necessary threshold. It's crucial for maintaining flow on city expressways and accessing all the primary roads in international markets. Anything less, and the car is seen as a barrier limiting its utility.
And acceleration. This is key for driver confidence, isn't it? Especially in dense urban traffic.
Urban confidence is everything. We measure it by 0 to 50 kilometers per hour in 5.0 seconds or less. This gives you the torque and responsiveness you need to confidently merge, change lanes, and pull away from traffic lights ahead of most combustion cars. It makes the car feel modern and capable, not sluggish.
And that performance is what necessitates that 30 kilowatt peak power requirement from our 96-volt architecture.
That's the link, yes.
Okay, now, the efficiency challenge. Getting under 9.0 kilowatt hours per 100 kilometers. This is the white whale of the project. How do you do that, given the need for a 100 kilogauge?
It's about optimizing 3 interdependent systems at the same time. 1, exceptionally low drag aerodynamics, a sleek profile, minimal protrusions. 2, mandatory specification of low rolling resistance tires, which can account for a huge portion of energy loss.
And 3.
And 3, the already mandated, highly efficient, permanent magnet synchronous motor powertrain, which has to be optimized for partial load operation. We are fighting for fractions of a kilowatt hour here.
And using our LFP chemistry, what does that efficiency translate to in terms of battery size and range?
We define 2 packages for market flexibility. The standard range pack is 15 kilowatt hours, targeting about 170 kilometers of real-world range. Then there's a long-range package at 20 kilowatt hours, targeting around 220 kilometers.
And the 20 kilowatt hour option is key because it gets you over that 200 kilometer threshold for tax incentives in a lot of markets.
Exactly. It's a vital option to have.
Okay. Safety and structure. This seems like a critical decision point. Abandoning the tube.
Yes. This is a fundamental systems engineering choice. We are formally, completely rejecting the structural standard of the low-speed vehicle world, which is the tubular frame.
Why the outright rejection? I mean, it's cheap, it's simple, it's served the segment for decades.
It's cheap, but it's incapable of meeting modern crash standards. Euro and CIPP proved that. And beyond that, it relies on complex jig work and manual welding, which is the complete opposite of our mandate for car spec lean manufacturing and high automation. So we're switching to a hybrid skeleton strategy.
Okay, break that down for me. What is a hybrid skeleton?
The platform is split into two parts. The underbody is a monocoque-like stamped steel platform. This gives us critical, rigid mounting points for the suspension and, most importantly, forms a protective bathtub structure for that big, flat battery pack.
And the upper body?
The upper body is the safety element. It's a cage structure built using closed-section, high-strength steel profiles, either stamped or roll-formed.
So you get the rigidity of a stamped platform where it matters: suspension, battery, and the lightweight cage structure overhead. What are the material specs for that cage?
We need over 60% HSS utilization overall. But the key areas, the A pillars for frontal impact, the B pillars for side impact, the door sills, they must use hot-formed steel. This is ultra-high-strength steel, over 1,000 megapascals of tensile strength.
And that's non-negotiable.
Completely non-negotiable. Without 1,000 MPa steel in those pillars, the survival space collapses in a 50 kph crash, and the entire project is a failure.
And to make that 2+2 layout truly viable, what passive restraint systems are we mandating?
A mandatory driver airbag cost constraints make a passenger airbag optional in the base model 3-point seatbelts for everyone and ISOFIX child seat anchors in the rear. This ensures the primary function, which is transporting small families, is done safely and compliantly.
All right, let's get to the heart of it. Part 4. The 96-volt high-voltage powertrain architecture. The sweet spot.
This is the core of our engineering decision. The choice of the 96-volt nominal platform, which peaks around 115 volts, is the strategic core of the whole SOR.
Right.
It's where we balance cost, efficiency, and safety perfectly. We've found the cost inflection point.
Okay, let's play devil's advocate. Let's start by definitively eliminating the alternative. Why does a low-voltage 48-volt system, which is used in basic microcars, fail our mission here?
It's all about power and current. We need 30 kilowatts of peak power to hit our performance targets. At 48 volts, if you do the math, power equals voltage times current, you need a staggering 625 amps for that peak.
625 amps, that's an enormous amount of current. What does that do to the hardware?
It demands massive, thick, heavy, and very expensive copper cabling throughout the entire vehicle. That bulk increases the cost and, crucially, the weight, making our 750 kilogram curb weight target just impossible.
And the heat must be a nightmare.
The IR heating losses, the joule heating, would be unacceptable. The thermal management of the cables and connectors becomes an immense engineering liability. It destroys both our efficiency and our reliability targets. 48 volts is functionally limited to vehicles needing less than 10 kilowatts.
Okay, so 48 volts is out. Conversely, why is the standard 350 to 400 volt EV architecture overkill for this segment?
Component cost, plain and simple. Stepping up to 400 volts requires expensive, high-tolerance power electronics, specifically 650-volt rated IGBTs or silicon carbide switches for the inverter. These components are necessary for 400 volts, but they are way too costly for a vehicle targeting this level of affordability.
And there's more regulatory overhead, too.
Layers of it. Complex insulation monitoring, extensive interlocks, specialized protective circuits. It all adds cost that the micro EV margin just cannot bear.
So the 96-volt system, peaking at 115, solves this by using a specific class of cheaper, better components.
Precisely. This is the component inflection point.
Yeah.
At this voltage, we can specify cheaper, industrial-grade 150 to 200-volt power MOSFETs for the motor controller, instead of those high-voltage IGBTs.
And MOSFETs are more efficient at this level.
They offer significantly lower conduction resistance and lower switching losses, which translates directly into higher system efficiency and less heat. This one choice is estimated to save 20% to 30% on the cost of the electrical control unit alone, compared to a 350-volt system.
And what does it do for the current management?
It cuts it in half. That same 30 kilowatt peak power now only requires 312 amps. This lets us use standard gauge, lighter, and less expensive cables, reducing both material cost and vehicle weight.
Okay, now safety. 96 volts is a B-class voltage. It's over 60 volts DC.
Good.
What are the safety compliance rules?
We have to comply with UNR 136, the EU reg for high voltage protection, so this means standard safety measures. The distinctive orange wiring harnesses, and a robust high voltage interlock loop, or HUIL system. But crucially, the insulation and creepage distance requirements are far less complex than for a 400-volt system, which helps us maintain that low bill of materials.
Okay, let's move to the battery system itself, the REES. We've established LFP chemistry is mandatory. Let's detail the pack spec.
LFP is the default. It satisfies our three primary constraints. Cost, we're targeting under $75 per kilowatt-hour longevity with a cycle life over 2,000 cycles, in compliance with that 2-hour thermal propagation rule from China.
And to cram as many cells in as possible, we're using cell-to-pack or CTP design. How much space does that save, and what's our density target?
By eliminating the traditional rigid modules and integrating the cells right into the pack tray, we gain 15 to 20% volume utilization. It's a huge efficiency gain. We're mandating a minimum system energy density of over 130 watt-hours per kilogram for LFP CTP.
And the electrical configuration?
Simple and robust. 30S, or 30 cells connected in series, to achieve our 96-volt nominal voltage.
Now, thermal management. This is often skimped on in budget EVs, but that kills longevity. How are we handling cooling, especially with that fast charge requirement?
We cannot compromise here, at least not on the high-spec version. The base model might get away with passive air cooling for low-rate charging in mild climates, but the long-range fast-charge-capable version absolutely requires liquid cooling plate, or LCP, integration.
And that's non-negotiable for DC fast charging.
Completely, because DC fast charging requires a high C-rate charge rates greater than 1C, and we need to support a 35-minute charge from 30 to 80%. That process generates a lot of heat. The LCP, circulating a water glycol mix, is the only way to reliably keep the cell temperature below 45 degrees Celsius.
And if you go over 45 degrees,
you dramatically accelerate cell degradation. You kill that 2,000 cycle life expectancy. The LCP is an investment in vehicle longevity and consumer satisfaction.
And the battery management system, the BMS?
It has to be car spec and robust. It needs to meet ISO 262622 ASIL-C functional safety standards, and we require active cell balancing. It's a complex system managing the health of 30 cells in series, making sure no single cell drags down the whole pack.
Let's move to the drive unit and charging. We've locked in the motor type, PMSM. Justify that choice one more time against that efficiency target.
PMSM is mandatory because of its efficiency profile. It boasts efficiencies over 95%, and it's especially good at low speed and partial load, which is what defines urban driving. That efficiency is the single most important factor for hitting that sub-9 kilowatt-hour consumption target.
And the spec for it.
We mandate a minimum 2-in-1 integration motor and reducer together to save space and weight. Rated power of 15 kilowatts, peak power of 30, delivering over 90 newton-meters of torque.
Okay, let's tackle the biggest technical headache of the 96-volt architecture, DC fast charging. How do we make our little 96-volt pack compatible with standard DC chargers that operate between 200 and 750 volts?
This is the major systems integration hurdle. If the car just relies on the charging station, we risk incompatibility with a lot of older stations. The VTS provides a highly creative solution that leverages existing hardware to keep costs down.
What's the engineering trick?
The VTS requires the electric drive system, the EDU, to incorporate an internal boost mode functionality. So instead of adding a separate, costly, high-power DC to DC booster component, we use the motor's own internal inductance and circuitry, along with the motor controller, to step up the low battery voltage internally.
So the car is effectively tricking the DC charger by using its own motor hardware as a temporary step-up transformer.
Essentially, yes. We utilize the power devices that are already in the inverter to achieve the voltage conversion. This eliminates the need for redundant, dedicated boost converters. It saves immense cost and complexity, and it ensures reliable fast charging. It's a crucial design innovation.
That's brilliant. And what about the auxiliary systems?
We need a DC to DC converter, 96 volts down to 12 volts, rated about 1 to 1.5 kilowatts. That powers all the low-voltage systems: lights, wipers, power steering. And crucially, the SOR mandates integrating that DC-DC converter into the onboard charger, the OBC, as a 2-in-1 unit.
Again, packaging and cost efficiency through integration.
Always.
All right, part 5. We've defined the structure and the power unit. Let's move to the running gear. With a short wheelbase and a 100 kph top speed, stability and handling are huge concerns.
They are. And stability and low cost are our guiding lights here. For the front suspension, we specify the standard McPherson strut setup. It's cost-effective, it's proven. But the VTS explicitly demands optimization of the anti-dive geometry.
Why so much focus on anti-dive for this segment?
Because micro EVs, with their short wheelbase, are extremely susceptible to nosedive under aggressive braking. It destabilizes the vehicle, and it really erodes driver confidence at high speed. By optimizing the anti-dive geometry, we make sure the suspension resists that pitching moment during braking. It keeps the vehicle stable and predictable.
And the rear suspension. Always a compromise between cost and comfort.
We have to avoid the extreme cost-cutting of simple leaf springs. They just compromise comfort and handling too much. but we also have to reject expensive independent suspension.
So what's the middle ground?
The optimized solution is a 3-length trailing arm with a panhard rod. It's a robust, solid axle structure. It's cost-effective, easy to package around the rear-mounted motor, and very durable. It provides a good balance.
And for steering, what's the assist system?
Electric power steering, EPS, is critical. It has to be. At 100 kilometers an hour, the steering needs to feel firm and direct. EPS allows for speed variable assistance. You get maximum effortless assist at parking speeds, and it dials back to minimum assist at highway speeds.
Okay, let's move to the electronic backbone. What's controlling this complex interplay of power, thermal management, and safety?
That's the job of the Vehicle Control Unit, the VCU. It's the central brain. It manages everything from torque arbitration, how much power goes to the motor-to-energy flow, the complex thermal loops, and all the diagnostic logic. It has to be built on automotive-grade 32-bit microcontrollers like the Infineon RX family.
And since we're referencing M1 car safety standards, software safety is non-negotiable.
Absolutely. The software architecture has to achieve ISO 26262 functional safety standards, targeting ASIL B or C compliance. This is necessary because of the potential risks. Specifically, you need rigorous software controls to prevent unintended acceleration. A 30-kilowatt motor can be lethal if it runs away unexpectedly.
Now let's talk about the cabin and a huge cost-saving innovation. The BYOD strategy. Bring your own device. We're canceling the traditional infotainment screen.
This is a direct answer to the high cost of embedded systems. A traditional automotive-grade IVI screen and processor can add $200 to $400 to the bill of materials, plus ongoing software licensing and obsolescence risk. We just can't afford it.
So what does the VTS specify instead?
It specifies a robust, high-quality, centrally mounted universal phone cradle. It has to integrate USB-C charging and, importantly, include a robust connection to the VCU, like Bluetooth or Wi-Fi. We then offload all the display functions to a dedicated companion app on the user's phone.
And what does the app handle?
Everything non-essential to driving. It displays the state of charge, calculates range, handles navigation using the phone's GPS, media, and remote functions like preconditioning.
And the payoff is huge.
Immense. We save significant hardware cost, and the vehicle benefits from being perpetually current. The user upgrades their high-res display and processor every 2 years, way faster than any car manufacturer can. It's a win for cost and for user experience.
Okay, part 6. This is where we translate strategy into reality. The supply chain and the SOR framework. How do we turn these technical specs into concrete demands for our suppliers?
The SRRs, the statements of requirements, are the contracts. They guarantee performance and ensure we can actually execute our 24-month industrial roadmap.
Let's start with the integrated EDU, the drive unit. What are the key requirements we're putting on that supplier?
Our demands have to be exacting. We're not just asking for a motor. We want an integrated, robust system designed to operate efficiently at that 96-volt peak power.
So what are the performance metrics they have to guarantee?
We require peak power to be 30 kilowatts or greater at 96 volts DC, with a peak torque of 90 newton meters or more. And we demand a maximum system efficiency of 94% or better across the typical urban driving cycle.
And what about durability and NVH noise, vibration, and harshness?
Durability is defined by the B10 lifetime requirement. The point at which 10% of the units are expected to fail must be greater than or equal to 150,000 kilometers. For NVH, the system noise has to be less than 75 decibels at 8,000 RPM. We have to control that modal whine.
And the interfacing demands.
A strict definition of all interface points, the cooling ports, the precise output shaft spline specifications, and mandatory integration of the high-voltage interlock loop sensor connections.
Now, for the high-voltage battery pack. The SOR there must be dominated by those global safety mandates.
It is. The supplier has to guarantee dual compliance. UNR 136 from the EU, and that highly aggressive GB 388-0301-2025 from China.
So reiterate the specific technical challenge of the Chinese mandate for the supplier. What do they have to prove?
They have to prove thermal propagation mitigation. After a single-cell thermal runaway, their design has to ensure the fire or explosion does not spread beyond that initial cell and does not compromise the pack structure for more than 120 minutes. This is the difference between a compliant pack and a death trap.
And what about physical protection, given the urban use case?
System energy density has to be over 130 watt-hours per kilogram for the LFP CTP. And protection against the environment is IP67 rated. That means it has to withstand 30 minutes of immersion in 1 meter of water. That's vital for flood protection.
Okay, let's get to the McKinsey angle. The cost optimization and industrial roadmap. How does our smart core platform design maximize profitability?
It creates instant modularity. We use the single architecture to launch two distinct product variants with minimal unique tooling costs. For the EU, we create an L7E version. By implementing software limits on power and speed capping it at 15 kilowatts and 90 kph, and using simplified safety configurations, like fewer airbags if the regs allow. This is our low-cost version for restricted European cities.
And the global M1 or AZERted version provides the full utility.
Right. That version has the software limits removed. It gives you the full 100 kph capability, the mandated full airbag suite, and the liquid-cooled fast charging as standard. The commonality across the platform minimizes parts inventory, validation effort, and most importantly, overall capital investment.
We've hinted at cost savings throughout. Let's quantify the biggest industrial cost saving.
Well, the 96-volt system alone should reduce the cost of electrical controls and wiring by 20 to 30% compared to a 350-volt equivalent. But the most profound cost saving in the entire industrialization project comes from the body strategy.
Using native color engineering plastic for the outer panels.
And by doing that, eliminating the paint shop entirely.
How big of a saving is that for the production facility?
The paint shop is typically the single most expensive capital investment in any car plant. It can be 30 to 40% of the total manufacturing capex, with huge ongoing OPEX for energy and chemicals. By designing a structural platform that's covered by pre-colored plastic panels, we eliminate that entire costly process. That radical reduction in industrial footprint is what makes this car economically viable.
Finally, the timeline. This is an aggressive launch schedule. What does the 24-month V model timeline look like?
We're aiming for start production SOP at month 24. It's rapid, and it's only achievable with parallel engineering. We have to lock down the concept freeze by month 4. That's followed immediately by aggressive supplier sourcing, months 3 to 6.
And you're prioritizing specific suppliers.
We prioritize technically mature and cost-effective Chinese suppliers, like Guoxuan or CETL for LFP cells, Invents for drive units, because they've already mastered the 96-volt architecture. Then design, detailed CAD, and rigorous crash and NVH simulations run concurrently from months 6 through 12.
A 2-year SOP timeline demands 0 major technical errors. It really underscores why this initial VTS and SR definition is the most crucial document for the entire project.
Absolutely. The rigor of the VTS prevents costly, time-consuming iteration later in the process.
What a deep dive. I mean, it is so clear from this that the toy car era for micro-EVs is completely, totally over. The future demands a vehicle with the structural integrity and the efficiency profile of a real car, even at the lowest cost point.
And that new foundation is defined by that high-rigidity cage structure, getting away from flimsy tubular frames, the non-negotiable stability and cost of LFP chemistry, and, critically, the technical genius of the 96-volt architecture.
That voltage choice really is the linchpin. It's what allows high utility, like 100 kph capability and aggressive efficiency, to coexist with a viable cost structure.
It is. The optimization formula defined by this VTS, the 3.1 meter length for crush zones and 2+2 utility, that 100 kph top speed, the brutal efficiency target, that is what separates a successful global product from an obsolete niche vehicle.
It just shows how regulatory pressure really does force this kind of revolutionary integrated engineering.
It does. We've examined how we optimized every single part of the system, electrical, mechanical, supply chain, to meet the demands placed by markets like China and the EU. This whole project demonstrates that engineering at the margin, where every dollar and every watt counts, is what drives the most radical innovation.
Which brings us to our final provocative thought for you to mull over. We've established that 96 volts is the optimal sweet spot for a cost-constrained urban 30-kilowatt vehicle, specifically because it lets you use cheaper, highly efficient MOSFET components instead of expensive IGBTs. The question then becomes, what happens further up the price ladder? The mid-range market, which is dominated by 400-volt battery systems today, is fighting similar cost and efficiency battles. So, if 96 volts is the micro-EV sweet spot, what is the next critical voltage architecture that will deliver a similar component cost reduction and efficiency boost for mid-range EVs within the next 5 years? Will the industry jump directly to 800 volts, or is there an intermediate inflection point, maybe 500 or 600 volts, that could optimize that balance between silicon cost and performance for the masses?
We'll leave you to consider those future electrical inflection points. Thank you for joining us on this deep dive.
Until next time, stay curious and stay informed.